In this video, we'll provide a high-level overview of the key processing steps involved in semiconductor manufacturing. The objective of this video is to provide an overview of the different stages of nano and microfabrication in semiconductor manufacturing. We'll do so by using two examples. In the first example, we'll describe the fabrication steps involved in mainstream silicon manufacturing, also known as complementary metal oxide semiconductor or CMOS technology. In the second example, we'll illustrate the versatility of nano and microfabrication by providing an overview of the fabrication process for creating a superconducting quantum chip. Now let us use CMOS microchips as examples to illustrate the fabrication levels in semiconductor manufacturing. Each microchip consists of many building block components called transistors. Transistors can be thought of as digital switches that generate 0 and 1 information bits. These switches are made of metal oxide semiconductor structures. The transmission electron microscopy TEM image here shows an example transistor where the nickel silicide and polysilicon layers form the gate electrode, SiO2 form the gate dielectric, and silicon is the semiconducting channel. In this transistor, the silicon germanium pockets on either side of the silicon channel are added to form source and drain regions, which complete the fabrication of transistor structure. As we'll discuss in this video, an iterative process flow will be used for realizing transistors. As the next integration levels, microchips are formed by connecting individual transistors using metal lines. Lastly, the semiconductor manufacturing allows these microchips to be replicated across a substrate. As a result, multiple copies of the same microchip are produced at once in a substrate. This capability is a hallmark of semiconductor manufacturing in driving down the cost of electronics. Microfabrication of a CMOS microchip starts with silicon wafer production. The wafer then undergoes an iterative workflow process consisting of lithography, deposition, etch, and doping. Once the microchips are fully fabricated, they are separated and individually packaged. In the following sections, we'll review these individual steps. The first step involves wafer production. The wafer is a substrate on which electronics are fabricated. There are various approaches for producing semiconductor wafers. A mainstream process for producing silicon wafers is called the Czochralski process. The image on the left provides a high-level overview of the growth process. In this process, the initial raw material is melted in a furnace and pulled into a single crystal ingot using a seed layer. The picture here on the right shows the ingot being sliced to produce individual wafers. As I mentioned earlier, transistors are the building blocks of microchips. Therefore, the fabrication cost of each transistor directly influences the overall cost of microchips. Note that microfabrication process allows simultaneous fabrication of transistors on the same substrate. Therefore, the cost of individual transistors is determined by the total cost of manufacturing divided by the total number of transistors on a substrate. This simple analysis indicates that increasing the number of transistors on a substrate is a key factor in reducing the cost of electronics. This has been achieved over years by increasing the size of wafers as shown in this plot here. While the diameter of early wafers was only 50 millimeters, over time the diameter has increased to 300 millimeters. The consequence of this progress has been the reduction of transistor cost. The red curve in this plot shows the cost of individual transistors, where the cost of transistor has decreased from nearly $1 per transistor to a very small fraction of a dollar. This is an incredible achievement, illustrating the positive impact of microfabrication on driving the economics of manufacturing. Note that the starting wafers are featureless. Therefore, lithography process is employed to print desired features for creating an electronic component like a transistor. We'll come back to the details of this process in a later video. On a high level though, the printing process involves the transfer of features from a lithography mask onto a photosensitive resist that is coated onto the wafer using UV light illumination. Fabrication of transistors and microchips also requires addition of new materials. For example, SiO2, polysilicon, nickel silicide, and silicon germanium. The process by which new materials are added during the fabrication process is called deposition. The deposition process can be classified into two general categories: physical vapor deposition, or PVD, through evaporation or sputtering of a source material, or chemical vapor deposition, CVD, through chemical reactions of different gaseous precursors. For example, silicon germanium pockets are formed through CVD by reacting silane and germane gases at elevated temperatures. On the other hand, the nickel silicide is formed through the PVD of a nickel film and its subsequent reaction with polysilicon at elevated temperatures. In a later video, we'll review the evaporation process as a versatile form of the PVD method. Once new layers are formed on a substrate, they may need to be patterned into a particular shape. The process of removing the excess material to shape the layers into desired patterns is referred to as etching. The illustration here shows the process of patterning. Once a film is deposited onto the substrate, the desired features are being printed through the lithography process. The patterned photosensitive resist serves as an etch mask where it is protecting the underlying deposited layers. The unprotected regions, however, are removed through the etch process, which subjects these regions to controlled chemical and physical attack. We'll review the etch process in a later video. Another key step in the fabrication of transistors is the introduction of doping impurities into the semiconductor material. The cartoon on the left-hand side shows an N-type transistor fabricated on a P-type substrate. The P-type denotes a semiconductor consisting of free positive charges called Hall's carriers. The carrier type and its concentration can be altered by introducing impurity atoms. For example, by adding sufficiently high concentrations of either phosphorus or arsenic atoms into silicon, it is possible to create N-type regions that have free electron charges. Alternatively, the concentration of the Hall carriers can be adjusted by adding boron impurities inside silicon. The incorporation of impurity atoms can be performed through either diffusion process or the ion implantation process. A main consequence of doping process is the ability to adjust the resistivity of semiconductors. The plot here illustrates how changing the impurity concentration in silicon alters its resistivity. In this plot, you notice that as the doping level increases, the resistivity of the silicon decreases. Lastly, once the microchips are fully fabricated across a wafer, they are separated using a mechanical or a laser dicing process and packaged individually into a microchip. This step concludes the fabrication of microchips in semiconductor manufacturing. As the second example, let us now go over the fabrication process of a superconducting quantum device called Josephson junction. As you will see in this example, the nano and microfabrication processes used in semiconductor manufacturing are adapted to fabricate these quantum devices. The first step involves the deposition of a multi-layer stack, which is typically performed through an evaporation process. This stack consists of superconducting aluminum and niobium bilayer separated by a thin alumina layer. Next, through a combination of lithography and etch, this material stack is shaped into a rectangular pattern. The next step forms SiO2 spacer regions, a process similar to what is used in fabricating transistors. To form the spacer regions, the SiO2 region first deposited through plasma-enhanced chemical vapor deposition onto the substrate, and then through an isotropic reactive ion etch, the spacer regions are formed. Finally, the top niobium electrode is formed through a combination of evaporation, lithography, and etch process. Individual Josephson junctions are then integrated into a quantum chip as shown in this photograph. This example illustrates the significance of nano and microfabrication for enabling manufacturing of quantum technologies.